That's what my computer can handle.
I'm sorry, I can't hear you super well.
Yeah, the microphone is a bit far away from where I'm standing.
Mhm.
Because it's also the speaker, so I want people to be.
Sorry, I didn't understand the last sentence.
Oh, it's fine.
I'm sorry, I can't hear you super well.
Yeah, the microphone is a bit far away from where I'm standing.
Okay, can people hear me now?
I hear you.
Yeah, we can hear you.
Cool.
We'll wait about 3 or 4 minutes for people to show up.
Okay, I will be right back in that case.
Okay.
One heads up is that I cannot seem to see the chat. My Zoom is just majorly acting up. So if people want to say something, they should feel free to just interrupt me during the talk.
I can also read the chat to you as it pops up, since I know it's hard to see.
Thanks.
Yeah, if there are any questions in the chat, Kristen will read them out to you.
Awesome. Thank you.
Okay, I'll give it one more minute to see if more people show up in person, and then we can start.
All right, I think we're ready to get started. So is the recording already in progress, Carolina?
Yes, it's already in progress.
All right, so in that case, I am super happy to welcome this week's speaker, Mila Chadayammuri from CFA. Mila has done a lot of amazing things, and I'm really excited to have her here. She got her undergraduate degree from Brown University in 2013 and then went on to do her master's and PhD at Yale, where she graduated in 2021. And she is now a postdoctoral fellow at the Harvard and Smithsonian Center for Astrophysics. And in addition to a lot of the awesome research that she'll tell us about today, she's also done quite a lot of really amazing science communication and EDI work. So you should also feel free to ask her questions about those after her talk. But for now, please tell us all about supermassive black holes.
Thanks, Kristen. Thank you so much for inviting me to your department. I'm very sorry I can't be there in person. When you have an Indian passport, just visas are complicated. But I do want to just start by thanking both Kristen and Carolina for really going out of your way to make things as smooth as possible on your end, and for eventually giving me the option to do this remotely. I really appreciate it. So that said, today I would like to talk to you about two studies that I've done recently using the eROSITA telescope. Let's jump right into it. So the first thing that I did, and this paper has already been accepted and you can find it online, was looking at the circumgalactic medium of galaxies. So when you think about the circumgalactic medium, if you're familiar with this topic, you may know this iconic graphic representation from a review paper by Tumans and Peoples and work. And so the CGM is defined as the gas that lives between the central star-forming regions of a galaxy and the virial radius. So it's not what we traditionally think of as the ISM, right? But instead, it's rather this buffer zone between the ISM and the intergalactic medium. So as such, it's the transition zone, right? So on the one hand, you have accretion from the cosmic web that's like bringing baryons into the galaxy halo. And on the other hand, you also have feedback processes from the galaxy that are moving the CGM gas around. Now, depending on the kinetic energy in a particular feedback mechanism, you can either end up with what is called the galactic fountain, so where the gas gets recycled, sort of cycling in and out between the star-forming regions and the CGM. Or if you have enough kinetic energy, you can end up with outflows. So this way, baryons would be sent back out into the intergalactic medium, right? So the CGM is essentially this both a reservoir for the baryons that will eventually form stars in the galaxies, and also the site where the gas gets enriched via galactic processes. And eventually this is what could enrich the IgM. So it's a really fascinating place. It's also a multi-phase environment, and especially if you are thinking about the warm hot phases, so the higher temperature phases, these are very diffuse. And by nature of, I mean, you know, when you think of a diffuse medium, you're essentially thinking of something that has low inertia, it's easy to push around. What this means is that this phase of the CGM is going to be nice and sensitive to different feedback prescriptions. So we can look for this in several different ways. I'm gonna briefly describe two and then focus on one. So on the one hand, you can conduct these idealized experiments, such as this one that I'm showing by Drummond Fielding back in 2016, where you can have an idealized simulation of a galaxy, right? And then you can vary one feedback parameter at a time. So you could say, okay, I know that stellar feedback operates often through winds, and these winds have a certain mass loading factor, which is essentially how much mass they carry along with them. And so you might vary just that one parameter at a time. You might just vary the mass loading parameter of your stellar winds. Now you could do that, and then you could look at what that does to the temperature and density profiles of the hot CGM in your super idealized galaxy, right? And while that is far more simplistic than anything that could really happen in the universe, it's a controlled little experiment that allows you to understand what's happening. So that's the kind of study that's presented here and on the top, right? And so you say, okay, if you increase your mass loading factor, you know, your temperature, actually, it's not a linear relation at all. It turns out it also depends on halo mass. But let's just say that you can see that varying one parameter in your feedback model already has significant implications for what the CGM looks like. But on the other hand, we know that there's multiple feedback processes acting at the same time in galaxies. So the other approach would be to turn to cosmological simulations like TNG, Eagle. There's a whole host of these out there at this point. And so you could look at, you know, you could start with acknowledging that these all have different prescriptions for stellar and AGN feedback, or that is supermassive black hole feedback. And then just look at the net effect. So say, okay, if I have galaxies from, in this case, for example, this is a study by Ben Oppenheimer published in 2020. So, you know, here he shows all the, you know, Eagle galaxies on the top, TNG galaxies at the bottom. And he, you know, you can by eye already say these two simulations are different. So then you can just do this comprehensive study of what does this these different feedback prescriptions in a cosmological context do to the CGM, right? In total. So this paper by Ben was really the motivation for our study. He's actually the second author on my paper. And so the idea was, okay, Ben has done these very detailed predictions from these two cosmological simulations. So let's try to do pretty much the same test observationally and see which of these two simulations is in better agreement with the observations. Why was now a good time to do this? Well, last year saw the release of the a test field from the eROSITA telescope. Now, eROSITA is essentially a 30-year improvement on the previous X-ray all-sky survey, which was ROSAT. And so you have probably seen thousands, if not tens of thousands of papers in the X-ray community written from this image right here. So this is the ROSAT all-sky survey. And then now with just the first of 8 scans of the whole sky with eROSITA, we have this, right? And so I'm just going to go back and forth. This is the sort of improvement that we're talking about, and it's only going to get better from here because so far already the survey has completed 4 scans, each of which is as deep as what I'm showing you right now. And so the net result is going to be, you know, if the survey completes 8 complete scans of the sky, then we're going to end up with 30 to 50 times better sensitivity than ROSAT, right? Now, one thing that I should mention at this point is that the circumgalactic medium, it's diffuse. It's actually, it emits photons in the X-rays, but just barely. And if you were to look at individual galaxies, we have detected the X-ray CGM of nearby galaxies. They tend to be the most massive and the most nearby, right? So that's a really biased sample. So while informative, it is biased. So what we're trying to do here is to collect a representative sample of galaxies. Now, if you are looking at galaxies that are not particularly bright or particularly close, you might end up with a situation where the signal from the galaxy is comparable to the noise. So I was talking to some grad students earlier today about X-ray astronomy. The main challenge is that X-ray photons are very scarce. So we work in the, in the Poisson statistics regime, right, where you deal with individual photons. So what I'm going to show you here is what happens when you stack images. So I'm going to keep flashing on the left a new image, each of which has a signal to noise ratio. So a signal that's about 5% as strong as the background. And then on the right, what you're going to see is the images adding up. Okay, so at this point, I would be very impressed by any of you who can see what the signal is. But I'm just going to keep adding images. And the thing is that the noise is random, right? The noise is Gaussian. So when we add up pixels, on average, the noise will cancel out, but the signal is going to keep adding up, right? And so that's how, by the time I've stacked even a handful of images, the signal is very clear to you, right? Somebody asked me at a previous talk if this was an actual image in the sky. It is not. We unfortunately do not have such beautiful disks in the sky, but this is just to illustrate the point, right? This is why stacking images allows us to enhance the signal to noise ratio of our observations. So that's what I'm about to do here, okay? So, but when you stack things, you can't just stack random points in the sky, because then you might as well be stacking noise, right? So you want to select the regions that you're stacking. You want to select regions where you expect a signal. So what you're seeing here in the purple are these dots. These are all galaxies from the Sloan Digital Sky Survey. I'll get into that in just a moment. Before I actually cut out the X-ray, let me describe a few more things. First of all, what we're looking at here is the first data release from the eRosita team. So this is not the all sky survey that I showed you a little while ago. Rather, it is a test patch that is a much smaller area. It's 140 square degrees, very, very, very small fraction of the entire sky. However, this survey was completed in just 3 months and has the same depth as the all sky survey will have after 4 years. Okay, and so essentially the idea with this was to provide a set of products to the community. This is all open access. So to provide some data products to the community that would allow us to do these science projects, right? Like test out these different ideas that then we can apply the same pipeline to the all sky catalogs as and when they come out. So we're working with this eFEDS patch, pretty uniform X-ray map. And then the purple dots are the galaxies. And then you might notice these white holes here and there. So what's going on over there is that usually when you're an X-ray astronomer, so for example, here at the Chandra X-ray Center, most of the science is either galaxy clusters or like X-ray binaries and supermassive black holes, okay? So you either have like the regions around very compact objects, or you have extended sources like galaxy clusters. These are the things that really emit a lot of X-rays. So if you have either a point source or a galaxy cluster in your stack, that is going to dominate your signal and not actually tell you anything about the galaxies that you were trying to learn about. And so in particular, the reason this is important is that the galaxies that we're talking about, they live in halos. So, from the stellar mass, you can use scaling relations to roughly estimate the halo mass. From the halo mass, you can estimate the virial temperature, and the circumgalactic medium is, you expect it to be at the virial temperature of the halo. And turns out that's going to be roughly this band over here. Now, this is the cooling curve from collision ionization equilibrium. And what this is telling you is like, what are the cooling processes that dominate at each temperature, okay? So for these galaxies, you're gonna be dominated by metal line cooling, which goes as density to the first power. And I'll also note that, these, depending on the metallicity of your gas, this tends to be lower even per number density, than the Bremsstrahlung value. So now thermal Bremsstrahlung is a it's a 2-ion process. So you may remember that Bremsstrahlung is basically when you have an electron, it's passing by an ion and it decelerates, and in that deceleration process it emits a photon. So this depends on the number density of the electrons and the ion, so it's density squared. Okay, so not only are you dealing with a lower emissivity per unit density in the galaxies than in galaxy clusters, but also this emission scales as density, and this scales as density squared, and galaxy clusters are definitely more dense than galaxies. So all of this is to really hammer in the point that you don't want to include galaxy clusters in your stacks if you're trying to get at the galaxy emission. So I was really conservative and masked out, like, let's see, twice the radius within which the galaxy clusters show any signal. Right? Because I just really don't want that contamination. Now let's move on to the galaxies themselves. So first of all, this is basically all motivated by Ben's paper in 2020. So we have galaxies with stellar masses from 10 to the 10.2 to 10 to the 11.2 solar masses. So basically a few times 10 to the 10 to a few times 10 to the 11. And then, so we split them right down the middle and call them the low mass stack and the high mass stack, okay? Within each stack, we split the galaxies into thirds by specific star formation rate. So this is the star formation rate divided by the stellar mass. If you plot them, you see that they follow this kind of bimodal distribution. And so we split them into thirds, and then we call the top third the star forming subsample and the bottom third the quiescent subsample. And the middle third, in most analyses, we just throw out entirely. So on the one hand, this means that we're losing signal, but on the other hand, this means that we have two very distinct populations. One where star formation is still ongoing, and one where it's definitely been gone a very, very long time ago, right? So this is a sort of sample that we end up with. Everything that we selected is between a redshift of 0.01 and 0.1. If it's below 0.01, probably would have been detected individually. If it's beyond 0.1, we're probably just adding noise. So that was the reason for our selection. And on average, our galaxies live at around a redshift of 0.07. And so overall, we end up with about 2,700 galaxies that are split like so between the low and the high mass samples. And always by construction, the star formation and the star forming and quiescent substacks will have the same number of galaxies because they're just thirds, right, of the whole stellar mass sample. Okay, so here's the preliminary by eye result, right? So we have star forming galaxies on top and quiescent galaxies at the bottom. We have the lower stellar mass here and the higher stellar mass here. Right now, this image is just background subtracted. There's going to be a lot more manipulation that we do going forward. The background is shown by the area between these two circles. So this is the background region. So essentially, what you do is for each, so you essentially compute the background for each source individually. And then you take the average over the entire stack. This is basically just to make sure that you're not computing an artificially high background because one galaxy had a bright object nearby. You always take the median. And so you compute the background, you subtract that from your stacked image, right? So that's all we've done so far. But there's many things that could potentially that could explain this. That is not just that the CGM is different in these things. So the rest of the study is about testing these alternate explanations. And just before we get into that, I will also note how we do the theoretical side of this, which is that if you start with the TNG or Eagle simulations, you go to a certain galaxy halo, okay? Then you select all the gas particles within 3 virial radii of the galaxy, okay? Now, for every gas cell or particle, depending on whether it's a repo or gadget, you're gonna know, you already know the density at temperature and metallicity from the simulation. So you use a software called PyXSim, which essentially predicts, calculates, right, how much emission you expect from each of those gas cells. Then you project those photons down a cylinder, right, that has a certain radius. So you used all the gas cells within a sphere, but then you're projecting down a cylinder. Again, you're just trying to mimic your observations. So that'll give you a sort of true incoming flux from each of these objects. Then you convolve that with the response function of a telescope like a Rosita to account for the fact that, you know, there's a point spread function, and, you know, these things are sitting at a certain distance away from the telescope. And then you also include how long the telescope is actually observing them for. So Ben went through this whole process in this 2020 paper using the numbers that are correct for the EFED survey, which we used. And so that's what we're working with on the theory side. So basically all the predictions that I show you from theory are stacked observations that have gone through this entire observation, this entire mock observational pipeline. So it really allows you to do an apples to apples comparison. And then the last major thing that we would worry about is, okay, so let's say you have a star-forming galaxy and a quiescent galaxy, right? Our sort of first pass over here is telling us that the star-forming galaxies are brighter in the X-ray than their quiescent counterparts. But one main explanation for this could be that we masked out all the point sources, so things that were individually identified as, you know, point sources. These would be either supermassive black holes in the AGN phase, or these could be X-ray binaries. However, let's say we didn't capture especially the X-ray binary population entirely. Often that might fall below the detection threshold of a survey like this. So what would happen is that those X-ray binaries, they would live preferentially in the central few kiloparsecs of the halo, because X-ray binaries are essentially the aftermath of dead stars, right? So you would expect to find them anywhere that you expect to find stars. So let's say the galactic disk might extend a few kiloparsecs, and I'll also check that that is in fact the kind of number that you get out of the SDSS photometry. That's the scale of these galaxies. So the X-ray binaries may populate the central few kiloparsecs, but the point spread function might take those photons and scatter them out to larger radii. Okay, so the way that we dealt with this was that we used scaling relations that are based on very high precision, so high spatial resolution observations, usually with Chandra, of nearby galaxies where you're able to resolve individual X-ray binaries, right? And so in that way, people have compiled these scaling relations that relate the X-ray binary brightness of a galaxy with relatively low scatter, although I will always acknowledge this is probably the most uncertain part of our analysis. Will relate the X-ray binary luminosity to the star formation rate and the stellar mass of the galaxy. And these two quantities we get again from the SDSS catalogs that have been doing, you know, basically stellar population modeling. So, okay, with all of that going forward, every time you see an observational value for the luminosity or surface brightness, you should know that I've already made a correction for what I expect the contribution from X-ray binaries to be. And that correction I applied using these scaling relations based on stellar mass and star formation rate, okay? And then one last small point that I will make is that, so here I show the TNG stacks in the green and the Eagle stacks in the orange. This is the X-ray luminosity from 0.5 to 2 keV. And this is the stellar mass. And one thing to note is the dotted line, so the dashed lines are the median value at each stellar mass, okay? The shaded region is the 1 sigma around the median. And then the solid line is the mean, okay? So this is something that I basically just want everybody in the stacking community to keep this in mind, where if you have any scaling relation that has significant scatter, so in this case, right, we're talking like an order of magnitude scatter around the mean in each case. If you take a stack, what the stack shows is a mean. So I want everybody to, like, whenever they make any conclusions from this, I want us to know that we're still we're still biased high compared to the median. So we're still preferentially learning about the brightest populations at a fixed stellar mass, or whatever it is that we choose to stack along. So that's just something that I want us to keep in mind when interpreting these results. Okay, with all of that out of the way, though, we are able to do apples to apples comparisons because we have these simulated mock stacks, and then we have our observed stacks. And so these are means, and they're both observed by eROSITA, right? And so the first result that I have is that the star-forming galaxies appear to be marginally brighter than their quiescent counterparts. This is true at all the stellar masses that I've looked at, which is basically 1 order of magnitude, right? So that is the first result. The second result is that if you look at the simulations, right, their star-forming galaxies at, we can say this in several different ways. Their LXM star relation is a lot steeper than what we observe, right? In other words, at low stellar masses, their, especially their star-forming galaxies, are a lot dimmer than what we see. I mean, you know, these error bars will shrink once we have more data, but at the moment, the quiescent galaxies seem consistent with the observations at all times. But yeah, essentially the simulations seem to be oversensitive to the stellar mass of the galaxy. In other words, the CGM in the simulations is reacting too quickly to the stellar mass of the galaxy compared to observations. So those are the 2 big results to start with. And now some of you may have seen a similar study from the eROSITA team themselves that used a very similar method but managed to come to the opposite conclusion. So they found that quiescent galaxies tend to be brighter than star-forming galaxies. Now, you know, because their paper came out like a month before ours, our referee wanted us to explain in great detail why we could do the same analysis and have different results, right? And I was basically able to show that this difference comes from 2 choices that we made differently. Probably the most important one is that, so as I said, I masked out everything around every cluster that was detected in the eFEDS field. So anything that was detected as an extended source by the eROSITA algorithm, I masked it out very generously. Whereas this study, which is Comparat et al. From earlier this year, what they did was they said that if a galaxy cluster has a redshift that is comparable to the redshift of their galaxy sample. In other words, if there was a chance that one of the galaxies of their sample lived in that cluster, then they would keep it, right? Let's recap. What this means is that they were including cluster galaxies. And also they removed anything that looked like a satellite galaxy. So that means that what you're left with is brightest cluster galaxies and brightest group galaxies, but mostly brightest group galaxies given the stellar mass. But those objects are known to be preferentially quenched, so they will only contribute to the quiescent sample and not the star-forming sample, right? So, and as I said, you're going to have a ton of emission always coming from clusters. So of course, your total luminosity is going to be higher if you're going to include something that's living in a cluster where you also have bremsstrahlung emission. So that's one thing that majorly contributes to this difference. And then the other thing is that they also integrated. So when they compute their luminosity here, right, they're integrating out to 300 kiloparsecs, whereas I integrate out to 100 kiloparsecs. This doesn't matter for the star-forming galaxies because those are not living in a cluster or group environment. Both things are the same. Whereas for the quiescent galaxies, the further out you go, the more ICM or the more intergroup medium you're including in your calculation. So simply put, this is essentially a different experiment. This is basically including a lot of baryons that are not in the galaxy halo per se, but are in the cluster or group halo as well. So this seems to be a big conversation in the field, so I'm just answering that preemptively. And lastly, for this part of the talk, I will pause for questions at this point. So the thing that we could really do with eROSITA that was impossible before with ROSAT is do spatially resolved profiles of the X-ray emitting CGM, Okay, so again, here I'm showing you the low mass stack, the high mass stack, the star forming galaxies, the quiescent galaxies. Okay, so now again, TNG is always shown in green, Eagle is always shown in orange, and you can see that the two simulations have different predictions for what the CGM should look like. So first I show you the profiles that are just background subtracted, right? Nothing else. This is just what you get from the images. Then I remove the contribution from low mass X-ray binaries. So this correlates with the stellar mass because low mass X-ray binaries form around, the zombies of low mass stars, which died a long time ago. So this just correlates with stellar mass. And then additionally, for the star forming galaxies, you have an extra correction for high mass X-ray binaries. Sorry, did I say for the high mass? I mean, for the star forming galaxies, you have to correct for the high mass X-ray binaries because that correlates to the star formation rate. Okay, so as you can see, the correction I have convolved with the point spread function, right? So basically this is the correction from the low mass X-ray binaries, this is the correction from low plus high mass X-ray binaries, because you basically take a certain quantity from the scaling relation and then you convolve it with the point spread function to see how it actually affects the radial profile. I think this is something that hasn't really been done in the literature before. And so, that makes a pretty significant difference in the inner regions about whether, say, you think TNG is doing a better job or Eagle is doing a better job. Okay, so that's what we have here. And so what do we see? Well, I think we see that the quiescent galaxies in the simulations are generally not emitting as much from their CGM as the observed galaxies. This discrepancy is probably the smallest for the Eagle high mass galaxies, right? But so what does this mean? So as I said, the emissivity depends on the density as well as the temperature, as well as the metallicity. So there's a few things that are convolved over here. And so, if it's line emission, of course, if the CGM in the simulations is not enriched enough, then it's not going to emit as much, right? But it would be rather strange to have a scenario where the high mass galaxies are in Eagle, for example, are much more enriched than low mass galaxies, enough to account for this kind of discrepancy. So I would say it's like plausible, but likely not the main reason. On the other hand, if you have, one thing to keep in mind is that these simulations, they all end up quenching their galaxies mostly by ejecting a ton of gas. So in Eagle, this is a thermal feedback prescription. In TNG, it's a kinetic feedback prescription. So both of them, what they do is they just remove a ton of gas from the star forming regions, and that's how they quench star formation. And so this is basically, I think, saying that they're relying a bit too much on that there should be a way to quench star formation without removing all the gas to such a degree. One thing to keep in mind is that, Eagle in the emissivity, it looks much better than TNG in this high mass stack, but Eagle is also known to produce much higher temperatures. So you could still have a problem of over ejecting the CGM in Eagle, but sort of coincidentally reproducing the surface brightness profiles because the gas is also too hot. So there might be too little of it, but it's too hot. And so the X-ray profiles look okay. So this is the kind of thing that would be really great to expand on with ERAS-1, where you have just many more photons, and you can actually do a spectral analysis. And if you can get a temperature map as well, then you can start to disentangle whether this issue, whether the temperature profiles are also consistent, because that's what you want. But at the end of the day, I'm going to note that we can say that the simulated galaxies seem to be, clearly have less luminous CGMs than their observed counterparts. Now, if you move to the star-forming galaxies, the star-forming stacks, right, then you're also likely to see a contribution from ongoing stellar feedback, okay? Now, first of all, again, in the high mass stack, I think the observations are pretty consistent with both Eagle and TNG. There are sort of like some radial bins where one simulation seems to do better than the other, but I think that overall, I would be hard pressed to pick a favorite amongst these two. But let's look at the low mass regime. And also one thing to note is that in the high mass halos, it's a higher mass halo, the gravitational potential well is deeper. And so feedback is going to be less able to push things around. So the effects are always going to be more sensitive in the low mass bin. So when we look here, right, in the central regions, let's look at the blue points, right? The central regions seem to have a slight preference for eagle, but I still think within error bars, both of them seem consistent. I find it very interesting that outside of about 40 kiloparsecs, the observations show pretty strongly an excess, like an emission far in excess of the simulations. And I couldn't make this go away by throwing out, like, the brightest galaxies. I actually threw out a lot of galaxies to see if this was just a contamination by a few weirdos. But it's not. It really looks like the observed star-forming galaxies in the low mass stack, they really do have a more extended CGM than the simulations predict. So this could be something like the stellar feedback in the simulations is actually not efficient enough. Like maybe in real galaxies, star formation feedback actually puffs things out, or maybe ejects material. It could be an asymmetrical process in any one galaxy, but if you end up stacking 400 galaxies, as I did here, what if each galaxy is shooting out a blob through a stellar feedback episode in some one direction? If you stack 400 of them in random orientations, you could end up with just like a radial profile that looks that has a higher value at these larger radii. So anyway, that's where we are with the circumgalactic medium. I'm gonna just show my conclusions for that part of the talk right here, which is that we find that star-forming galaxies are brighter than their quiescent counterparts. CGM X-ray luminosity increases with stellar mass. This is all expected. We find that the simulations, however, have a CGM luminosity that increases too quickly with stellar mass. And we see that the profiles, while they're in decently good agreement, I will note that none of these simulations ever calibrated to CGM properties because they were not available at the time that the simulations were designed. Given that, I think they agree decently well, but discrepancies remain, and I think these discrepancies could be telling about how to modify the feedback prescriptions in the simulations. So I'm going to stop there for phase 1 and take any questions on this paper before moving on to the next one.
I guess I have one question about your LMXP prescriptions, because I find it absolutely hilarious that the objects that you're masking out, your garbage, is basically what I have spent
your career on.
Yeah.
Yeah.
So do you feel like the prescriptions for how you can get rid of these guys, is that like pretty straightforward, or are there ways you feel it could be better?
Yeah, so this was actually, as I said, this is my biggest worry, because there are several papers in the literature. Brett Lamer, as seems to have done a lot of the most comprehensive studies with Chandra. So Lamer has a couple papers. There's somebody else as well. Mineo and Gilfanov at the Max Planck's in Garching have also done similar studies that are older. And there's actually a lot of uncertainties here because everybody publishes their scaling relations for a different energy band in the X-ray, right? So for example, here, this plot seems to show maybe it's bolometric luminosities, it's not even clear. But like one paper will cite the X-ray luminosity for X-ray binaries from 0.2 to 0.5 keV, which is what I have, right? Which is what I processed my images for. Another one will say it's for 0.8 to 10 keV. Another one will be like 0.5 to 5 keV, right? So, okay, you have this value in one energy band, but you want to convert it into the energy band that we're actually observing, right? So that requires you to have an understanding of the photon index of the X-ray binaries. And as somebody who studies X-ray binaries, you would probably know that there's a humongous range in these. Like, I've seen values ranging from 1.4 to 2.1. This is for some kind of power law spectrum, right? So this can cause a huge difference in the normalization of, of these lines, which is what I'm subtracting from this, right? And it's not always clear, which is the correct choice. And so what I did was I actually did the calculation using 3 different models and then just took an average and included the range in the error bars, just the most conservative kind of thing. But I would really prefer a better model. It looks like there's some sensitivity to the metallicity, right? So the X-ray binaries, you might have more of an X-ray binary population if you have, I think, I actually don't remember. You would be the expert
I
on
think
this.
more metal rich.
I'm sorry?
I think usually more metal rich helps.
More metal rich. I think it might actually be the opposite for some reason. I think the low metallicity galaxies seem to have a higher normalization for their X-ray binaries. So this is the Brett Lamert 2019 paper.
Oh, I think I know where we're getting mixed up, which is they look for globular clusters to find the low mass X-ray binaries. In the globular clusters, it prefers metal rich globular clusters, which of course has nothing to do with the host galaxy.
Gotcha. Yeah. So, there's all these kind of little details, and yeah, I mean, I don't really know how to address that. I mean, short of having some, incredible model for X-ray binary population that will tell you exactly what happens as a function of energy band, like rest frame energy band in the X-ray, as well as any easily observable properties of the galaxy, right? I think if we can get a better model for that, that would make this whole, that would change the game with this, and it would remove the biggest uncertainty, I'd say.
Cool. I feel like I could talk all day about this, but I'll let you move on and maybe I'll ask questions afterwards about this.
Sure. Does anybody else have any questions about this part? Okay, I'm going to move on to the next one in the interest of time. The next thing that I did also with the same eROSITA data was see if we could test models of the origin and growth of supermassive black holes. So for those of you, well, let's say for all of you, let's talk about where we think supermassive black holes may come from. So they're very different from like the stellar mass black holes, where we have like sort of this Chandrasekhar model of collapse. Supermassive black holes, there might be several different formation channels. They might have formed from population 3 stars. They may have formed from runaway collisions in nuclear star clusters. They may have formed through the direct collapse black hole scenario. So these are ranked in order of the mass of the seed. So this could be like about 100 times the mass of the sun, all the way to, say, 100,000 times the mass of the sun. You could have this huge range in the seed mass. But then, of course, these seeds happen at very high redshifts, right? Again, it depends on the model, but let's say, these are mostly happening at like beyond redshift 10. So if you have a high redshift seed, right, we're looking, at the end of the day, we're going to look at black holes that are at the present day, right? So that are relatively close to us. So they're going to have grown a lot in the meantime. And so, maybe that growth is going to be Eddington limited. There have been various models for how you can have super Eddington growth. Black holes also grow not just through accretion, but they also grow through mergers, same way as galaxies do. So depending on both the seed model and the dominant growth channel over cosmic time, what you will end up with is a different supermassive black hole occupation fraction, which is basically what fraction of galaxies at a fixed stellar mass and at a fixed redshift contain a supermassive black hole, right? So maybe, there might be some model, like let's say if it's a light seed model and the growth is slow, then, by redshift 0, what you have in the center may not qualify as a supermassive black hole. So that could put you with an occupation fraction of 0 at low stellar masses. Whereas if you have a direct collapse scenario and it's growing fast, well, then you're definitely going to end up with an occupation fraction of 1. But really, you're going to have something in between. Right. And so you can model this theoretically. There are many ways to do this, but my collaborators, Angelo Ricarte and Priya Natarajan at Yale, have used the semi-analytic modeling approach. So what they do is they select a distribution of halo masses at redshift 0, okay? And then they create merger trees. So basically this is like using the extended Press-Schechter formalism. They basically use they do, a random walk up the possible merger histories for each halo. And then they essentially, they generate about 20 realizations for each halo. They statistically construct a merger tree. Okay, so you basically have a bunch of halos that are connected, that basically over time merge with each other and eventually give you a distribution of halos at redshift 1. Now, at each of these snapshots, you will apply a scaling relation. Okay, so one scaling relation will allow you to go from the halo mass, which is the thing that you're starting with, to the stellar mass. Okay, so there are scaling relations that do this, may or may not include a redshift dependence. Now, once you have the stellar mass, you can use different scaling relations to, for example, figure out the effective radius of the galaxy, so how compact it is. You can use that, and maybe also the size. You can use other scaling relations to predict the stellar velocity dispersion in those galaxies. And then at this point, you have the famous M sigma relation. So the relation between the mass of the central black hole and the central velocity dispersion of the galaxy. So essentially, they're using all these scaling relations to populate these merger trees with black holes. Okay, now you have these black holes, and then the black holes grow over time. So they seeded black holes in a variety of different ways. Okay, so sorry, they don't use the scaling relation to populate this with black holes. They used it to populate it with M star and sigma. Then they seeded with black holes with two different models. Either they do a population 3 seed, which is low mass, or a direct collapse seed, which is high mass. And then over time, every time two galaxies merge, they assume a 10% probability that the black holes in them also merge. Okay, otherwise you just have two separate black holes. Now, so that's one way that the black holes grow. And then there's also the secular accretion mode, which is that if a black hole is not merging, they posit that it grows, it accretes at some Eddington rate. Now that Eddington rate will be pulled from so the Eddington rate is the accretion rate normalized by the Eddington accretion rate, right? So that's called the Eddington ratio, sorry. So they pull from some distribution of the Eddington ratio, some distribution of the Eddington ratio. Now this could be a power law, right? You could posit that the Eddington ratio is proportional to the star formation rate. So this is the AGN main sequence model. Or you could have a different tuning entirely that, I mean, this was a model that managed to reproduce observations of broadline quasars at intermediate redshifts. So basically you can have various analytic prescriptions for how the black hole accretes when it's not merging. Okay, so how the supermassive black hole is growing. So to recap, you seed black holes with different seed masses. So you can test either POP3 seeds, or like you test light seeds or heavy seeds. And then you also run the whole model a few different times, each time with a different prescription for how black holes grow when they're not merging. Okay, so essentially, what is the distribution of Eddington ratios of the black hole over time? And at the end of the day, what you're going to end up with is a catalog. So for example, here are Angelo's models. These are the POP3 seeds, these are the direct collapse seeds. And then I've shown you what, if at redshift 0, what those halos look like. If I just plot them in M star, in LX M star, right? X-ray luminosity versus stellar mass. And you see that they look quite different from each other, right? So then the question is, which of these best fits the observations? Now, again, comparing like thousands of points to each other is hard. So we look for some sort of summary statistic. And so that's why the supermassive black hole occupation fraction is so handy. So, but again, occupation fraction of what, right? So for example, if I just plot the fraction of galaxies that contain a black hole greater than 10 to the 6 solar masses, I get something like this. Okay, so the dotted lines have POP3 seeds, the solid lines have direct collapse seeds, the different colors are different growth models. So, okay, one growth model stands out from the rest, but otherwise you can't really tell the models apart from each other. But on the other hand, if I also ask for them to be luminous at redshift 0, right? Which is what would show up in any electromagnetic survey, then the models actually look quite different from each other. So these are the POP3 seeds. These are the direct collapse seeds. And these are two different seeds, but this is the model that managed to reproduce the quasar luminosity function at high redshift. I'm going to say this is unreasonable because this is saying that there are no luminous AGN at redshift 0, but for completeness sake, I'm including that in this study as well. And now this is something that we can measure, right? We can measure the occupation fraction of luminous black holes. So this is what we are essentially calling AGN in these galaxies. However, we need to be very careful about modeling the selection effects. So if you're, okay, let's think about this from a Bayesian perspective, or really let's just break down the logic of what's going on. So let's say you have a galaxy. Either it has a central black hole or it doesn't, right? So if it doesn't, of course, you won't see anything. Now let's say there is a black hole. We know that AGN have duty cycles. So sometimes they're on, sometimes they're off. If it's off, you're not going to see it. Okay, but if it's on, now it'll have some luminosity, which is going to be, proportional to its accretion rate. And then you want to apply bolometric corrections into, in this case, the X-ray. And so if the flux is below the detection limit of your survey, then of course you're not going to see anything. But if all these criteria are met, if there is a black hole and it is in the on phase of the duty cycle and its current flux is above the detection threshold, then you will have a detection. Okay. So you're convolving the occupation fraction, the duty cycle, and the Eddington ratio distribution. So we're going to model all of this. And so this is basically expanding slightly on Brendan Miller's 2015 work. So he did this work with Elena Gallo at the University of Michigan. And so you write down a functional form for this occupation fraction. And it's described essentially as a sigmoid function. It goes to 0 at low stellar masses and 1 at high stellar masses. And in between, it can either, grow quickly to 1. So if you have a light seed, for example, you expect there to be a supermassive black hole, even in very low stellar mass galaxies. But if you have a very, very heavy seed, then you don't expect it to happen. You don't expect to see it in all but the most massive galaxies. So, we want to figure out where in this regime the real supermassive black hole population lies. Now, so next we want to know if it is luminous and if it is above the detection threshold, right? So this plot is, again, this is from the Brendan Miller paper. So in that case, they had a survey that was very well designed and had so it looked at only near, like basically redshift 0 objects. So they had a very uniform luminosity limit. So they knew that they would only detect objects if they were above this value, right? So everything below this value was treated as an upper limit, and everything above, if it was found, it was a detection, right? So so you classify things as either detections or upper limits. Now you can do this in the space of LXM star. So that's basically the Miller 2015 paper assumed that you can model this relationship as a power law with log normal scatter. Okay, which is maybe true. Okay, I wanted to check how sensitive their results were to the assumption that that is the appropriate scaling relation. Like maybe that relation just doesn't exist at all. So I also tried a model where rather than M star, you have a power law relation between the X-ray luminosity of the point source and the central velocity dispersion. So essentially, this is like the first order model where you say the black hole is related to the velocity dispersion. Or you can go a little extra and actually assume that you have an M sigma relation. So I actually got velocity dispersions for all these galaxies. And so, you use the M sigma relation, which has already been measured by McConnell and Ma, Cormendi and Ho, all of those, and the intrinsic scatter to measure the black hole mass just directly from observations of your galaxies, and then convolve that with an Eddington ratio distribution function. So this is, for example, something that was measured in a 2017 paper, but I actually didn't assume this distribution at all. I just said, okay, I'm going to assume that it's described by some power law with some upper and lower cutoffs and some slope. So essentially what I'm doing is I'm trying 3 different models for the scaling relation between the extra luminosity and of the black hole, right, of the supermassive black hole, and the galaxy properties that I can measure. So, okay, so I'm running a little bit over time, but we also started late, and I will wrap up fairly quickly. So, okay, basically, again, we're using EFEDs, we use all these galaxies, we cross-match galaxies from the Gamma and SDSS surveys to the nearest X-ray point source. The point source catalogs were provided by the eRosita team. And here I plot the distribution of distances between each galaxy and the nearest point source. I considered something to be a match if the distance between the galaxy and the X-ray point source was less than 5 arc seconds, which is the astrometric precision of the eRosita point source catalog. Okay, so that's what we call a detection. Everything else I treated as an upper limit, given that I know the flux limit of the EFED survey. Okay, so then you end up with something like this, LXM star, or LX sigma. You can basically just plot the distribution. So here the solid points are detections and the faint points are upper limits. Okay. Once you have all of those, you basically run this entire Bayesian inference pipeline that is sampling the parameter space of your underlying model assumption, right? So let's say if it's an LXM star scaling relation, that scaling relation has a normalization, it has a slope, it has a scatter. And then finally, you're sampling this parameter M star O, which is tuning, which is telling you the shape of your occupation function. This is what we're after, okay? But you have to also jointly fit for all of these things. So you have an MCMC sampler that uses a PDF, a posterior distribution function that you've defined based on your physical model. This is, we have to assume that this is model dependent, and then maybe the data will tell us otherwise. And so, I ran this using all these different models, okay? And so the first result is that the first result I'll say is that the size of your sample does help. So even though the 2015 paper had Chandra, it has better spatial resolution, and the objects were all close by and so on, it had some survey design advantages, but we have 66 times more galaxies, and that alone was able to shrink the error bar significantly. So this black band is a 2015 result, and the blue band is our result, right? So using the same model, so using the LXM star scaling relation. So increasing the number of galaxies definitely helps with your inference, even if your survey is shallower, because we're able to incorporate upper limits as information. Next, the model that you assume does matter. So for example, this is the LXM star relation that the Amuse team assumed. But if you use an LX sigma scaling relation, your values sort of shift a little bit to the right. So you go towards slightly lower occupation fractions. But they're not super different. This is the model where you have an M sigma relation and a power law Eddington ratio distribution function. So here I assumed a duty cycle of 1. Here I assumed a duty fraction of 10%. This is really the thing that blew up the error bars, because if you think about it, what this is saying is, oh, well, if there's a 90% chance that the AGN is off, then the fact that I'm not seeing it isn't really telling me anything. So for all I know, there could be things here that are just off 90% of the time, right? So the assumption of your model matters. But at the end of the day, this is the model that matches the semi-analytical models that that Angelo and Priya ran. And so what you can do, oh, sorry, there's sorry, one more test that I was able to do is check the effect of how low in stellar mass do you need your observational sample to go to get meaningful results. And on the one hand, like, I really worry about stellar mass completeness. We can talk about that later. But the gamma sample is only stellar mass complete above 10 to the 10.4 solar masses. And at that kind of stellar mass, all the values of M star O, they kind of, a lot of them are going to converge to 1 at these high stellar masses, right? 10 to the 10.4 is around here. So you really want to have galaxies that are sampling this parameter space so you can start to distinguish between different models. So ideally in the future, we would want to repeat this with a survey that has more that has actually a complete sample at lower stellar masses. And lastly, I'm just going to show you the comparison with the semi-analytic models, which is the exciting part, I think. It seems to me that, the population 3 scenario is not really preferred with the observations because it requires you to have luminous objects showing up in galaxies at very, very low stellar masses, which is not the case. That's not what we see. Whereas the direct collapse seeds, they agree really, really nicely with the inferred black hole occupation fraction. This model was always kind of a bummer, so we can throw that away. I do think it's a little sad that we can't tell between the different growth models for the black holes. I wish that would have left more of a signature. But my guess is that, if we can repeat the study in the future by splitting the galaxies into samples by star formation rate, then we can start to test models like this, where the black hole rate is correlated with the star formation rate. You can essentially make a plot like this. At this point, it's just occupation fraction as a function of stellar mass for all galaxies. But in the future, sort of similar to my CGM study, we might be able to do this as a function of star formation rate or other properties as well. And that can help us test these seed and growth models in more detail. So that's where we are. This paper should be submitted pretty soon, and I'll just take questions at this point. Thank you so much for your time.
Yay.
Thank you.
That was a really exciting talk. So Nicole just put a question in the chat. She said, I feel like I only ever hear of discussions of galaxies having supermassive black holes at the center, but could a galaxy at the present day have a non-supermassive black hole or intermediate mass black hole at the center instead? Also, what's a BLQ?
Okay, so a BLQ is a broadline quasar. So this is a class of active galactic nuclei, but they're detected in the optical, and specifically that model was tuned to observations of broadline quasars at a higher redshift versus the population that I'm sitting here is closer to redshift 0. So that's a BLQ. Now, could a galaxy in the present day have a non-supermassive? Oh, okay. So let me check that I understand your question. So are you asking, what if there's a black hole at the center that's not like a supermassive black hole, but it's just like an intermediate mass black hole? It's like more massive than a stellar mass black hole, but maybe not quite a million or a billion solar masses. Is that possible? Is that the question?
Yep, that's the question.
Okay, great. So yes, the answer is absolutely yes. And so there have been teams like Vivian Baldassare, for example. Vivian is probably the most well-known for this, but there's various teams that have been finding ever lower mass black holes at the centers, especially of dwarf galaxies. So Anil Seth, his team also does work. I was just at a conference about this last week. So people are finding black holes down to, like, I think we're talking about like 10,000 solar masses is the lowest mass. I actually think it's a few times 10,000 solar masses are the smallest. They're still called intermediate mass black holes at the centers of galaxies. So that's why, like, using a cut like this, for example, I would say is erroneous, because then yes, you actually could have a model that in your dwarf galaxies is predicting a central black hole that grew from one of these seeds, right? It's just that the environment in a low mass galaxy is not conducive to grow it to quite such high masses. So applying a mass cut to your supermassive black hole population, and this can enter anywhere in your inference pipeline very sneakily. But if you make this kind of assumption, you're going to predict something that's quite different, right? So we always want to be very careful about what we're qualifying. And in my case, I'm trying to include intermediate mass black holes here as well.
Thank you.
Sure thing.
I guess for people on Zoom, if you have other questions, feel free to raise your hand or put it in the chat. And if nobody else has a question at the moment. I have questions about intermediate mass black holes.
Yeah, sure.
So yeah, I think that this is an area that I'm becoming even more excited and interested in. And my feeling is that people can be a little bit snobby about what they consider to be an intermediate mass black holes.
Mhm.
And so I think most of like the Amy Raines and Vivian, who you mentioned, the
I'm
black holes.
sorry, that was a huge oversight. Amy Raines is definitely
Oh, yeah.
a huge name in the field. Yeah.
Well, I won't tell her. I don't even know her. But I think the stuff that they've been finding has been sort of on order of like 10 to the 5.5
Mhm.
solar masses, which is, I feel like if you consider like people who like supermassive black holes, like they'll say it's too small. But then I was definitely talking to somebody about this, and they just said, do you think 10 to the 5 or 10 to the 5.5 should be considered an intermediate mass black hole? So I'm curious what your opinion is.
Okay, I think that if it's not a stellar mass black hole, then we don't understand how it formed, right? So I think that there's like some class of interesting objects that exists at, you know, honestly, if you ask a gravitational wave person, they will say that 100 mass black hole is an intermediate mass black hole, right? Now you will never find a 100 solar mass black hole in the X-ray. I mean, I doubt you would honestly, I mean, maybe with like a broadline with like a spectral analysis, but those spectra often have resolutions of, the resolutions place a sort of lower limit to the mass that you can detect. So even if you're looking for broadline quasars or something, electromagnetically, you're very challenged in finding objects that weigh less than 10 to the 4 solar masses. So realistically, I think, I think it's better to just be agnostic until we have the data. And at this point, I think all we know is that, the stars that we know dying is not the only channel to form black holes. And so I would say, if it's more massive than 10 solar masses and it's less massive than 10 to the 6 solar masses, then by all means call it an intermediate mass black hole. But then like maybe add context. So if you're a gravitational wave person, that might mean one thing. If what you're worried about is, is there some kind of like massive compact object that might provide feedback to your dwarf galaxy over cosmic time and that affects your stellar populations, that might mean something else, right? So I'm agnostic.
Cool. I think just because we're kind of getting close to the end of the day here,
Yeah.
we'll say thank you very much. And I would encourage people to follow up offline, online, offline after this as well. And I'm certainly going to be pestering you with questions. So thanks for joining us.
Yeah, sure thing. I think, Kristen is the easiest way to get my email, or if you know my name, I'm very easy to find online. So if you have any questions, please do contact me. And thank you for your time.
Another sad Zoom clap. Bye.
Bye.